You know that feeling when you have a project you're supposed to be working on, but then another idea pops into your head and just won't let go until you figure out if you can do it? Yeah, that happened to me this week. Again. Welcome back to Cloud42. I'm James. Well, you saw me putting together Gridfinity storage for all of my metrology gear, and I'm doing the same thing for my camera gear. This is my camera toolbox. Got my production monitor, sensor cleaner, some miscellaneous hardware here, and then the top drawer has all of the small stuff: GoPros, batteries, lens covers, filters, remotes, memory cards, and lens cleaning stuff. And one of the things that I want to have in here is a lens cleaning duster for, blowing dust off of the sensor or out of lenses when I swap them out on the camera. And this is the duster that I've been using. And this is just one that came in a kit with one of the camera lenses that I bought. And it works great. It just, when you squeeze it, it forces air out the top, and it's got a one-way valve in the bottom to suck air in. The problem is it's too big to fit in this drawer. It won't fit in a 1-unit wide Gridfinity space, which is what I would really like. But even if it did, it doesn't matter because the diameter is too big. It doesn't actually fit in the drawer. It actually hits the top and gets squeezed and rolled around every time I open and close the drawer. Now, easy solution is, which we never go for the easy solution, but the easy solution would be to just buy another one that's smaller. And I looked, and I spent a bunch of time online trying to find one of these that was smaller and would fit in a 42 millimeter wide space and be, 40 to 42 millimeters high, so it would actually fit in this drawer. And as far as I can tell, they don't exist. But then I got to thinking about it and realized this is just a flexible polymer. I've got flexible filament for my 3D printers. I see no reason why I shouldn't be able to 3D print exactly what I want. Is this a silly idea? Yeah, probably. But like I said, this sort of got into my head of, can I do this? And can I make something that is just as good as the commercial options? And I don't know. Let's go find out. I spent some time here in Fusion, and this is what I came up with. This is just a nice, smoothly curved bulb with a tip, and it's hollow with a 1 millimeter thick wall. Now, modeling something like this in Fusion is not nearly as complicated as you might think. In fact, you can see I've only got 4 features here down on the timeline. The way I always start a model like this, or really anything that I'm going to model, is with parameters. So I'll go into Modify, Change Parameters, and set up a few values that I know or that I think I know when I'm starting out. So I've put in a value for the tip diameter of 2 millimeters. That's the inside diameter of the opening in the tip. I have the wall thickness of 1 millimeter, and then the overall length. Now in this case, I want this to fit into a Gridfinity tray, and I'm allocating 3 units for that. So I've got 42 times 3, and then I'll subtract 10 millimeters from that. That'll give me 116 millimeters, and that will fit in a 126 millimeter Gridfinity tray. The max diameter for the bulb I want to be 40 millimeters, and that'll fit in a 42 millimeter wide tray, and that should give me enough clearance to get the drawer closed. Now, the first step for designing something like this is always to start with a sketch. And in this case, I am just sketching a center line, and I actually have used the center line feature. Thank you to whoever mentioned that to me in a comment on a previous video. And then I've drawn half of the bulb. And I've put in a few dimensions here. So here's the overall length of 116. Here's the tip diameter, and because I took the dimension from the center line to this point, it's now a diameter dimension, and this is just the tip diameter plus the wall thickness times 2. And then I've sketched out the shape that I want for the rest of this. The base is 25 millimeters wide. That seemed pretty reasonable. And I've got this necked down to a point that where it's 8 millimeters, and then I've got a couple of tangent curves that take it the rest of the way down. As far as the heights here, I'm just working off of the overall height. So the straight section here, I've got this defined to be the length divided by 5, so that's 1/5 of the height. And then for the distance down to this tangent transition, that's 1/3 of the height. And then for the overall dimension down here, this is just half of the maximum diameter. Now, for this diameter, you'll note that this is a radius dimension and not a diameter dimension. For whatever reason, if you take a dimension from a center line to a point, it'll automatically make that a diameter dimension. But if you take the same dimension and take it from a center line and then right click and say pick circle arc tangent and take it from the tangent point of a curve, it always creates it as a radius. If somebody knows a way to make that come up as a diameter, go ahead and throw that down in the comments and we'll all learn something. But for now, it's pretty easy. You just say max diameter divided by 2, and that gives me the basic shape of half of the bulb. So then we can just use the revolve feature. So this is up here, create revolve, and just select that profile, and it will revolve that around the center line. You don't even have to pick the center line because it's a center line and there's only one in the sketch. It knows what to do, and that creates the solid. Now, this is still a solid, and we need it to be hollow. And the easiest way to do that is just with the shell command. So we just click shell, click the tip that we want to be open, and then put in the wall thickness. And we'll just use the parameter that we created earlier, and that will hollow this out. So now we have a hollow bulb. I don't want this to be square on the top. I'd like to have a little fillet up there. So we'll just add a 3/4 of a millimeter fillet. I don't want that to go all the way to a sharp edge. Sharp edge can't really be printed, and in reality, there's just going to be, one extrusion around the top, but that'll make the top nice and clean. And that is the shape. We can just export this as an STL, load it up in the slicer, and print it. Now, I do want to make sure when this gets sliced that the wall is reasonable. I chose 1 millimeter for the wall thickness. I figured that would be 1 or 2 extrusions, and it looks like the slicer is doing 2 extrusions, and it looks like it's doing that pretty consistently from the bottom all the way to the top. I was a little bit concerned with the sort of gentle overhang that we have here in the shoulder area, that it might be thicker and it might try to fill that in, or that it might be messing around and changing the wall thickness, but it looks like that hasn't happened. The slope is gentle enough that this should print cleanly. This is the filament that I'm going to use to try to print the squeeze bulb. This is a flexible TPU, and this is an 85A durometer. So this is a relatively soft and relatively flexible filament. Stuff I normally print with is like a 95A or a 98A, the Ninja Tech Cheetah, and it's a lot firmer and it's a lot easier to feed in printers. This stuff's pretty floppy. You certainly could not run this in the AMS of a Bamboo Lab machine, but it runs pretty well in the Prusa XL with a few caveats. Now, this particular one is Soraya Tech brand. I don't know that that particularly matters. This is just one that I bought and had in my closet to try, and I've gotten really good results with this in the XL. I just went down and found another 85A TPU profile, and it just worked right out of the box. There are a few challenges with printing with this stuff. The first one is that it's very hygroscopic and it sucks up a lot of water. So you definitely have to dry this before you can use it. And even after you dry it, it's going to suck up water from the air while you're printing. So you really need to print this from a dry box. So to do that, I've got a bunch of different dryers that I've used over the years that I've been pretty happy with. But I've seen a few people using these Polymaker PolyDryers, and it's a 2-part system with a heater module on the bottom and a separate box for the filament. The idea being that you can put the filament in the box, put it on the dryer, run your dry cycle, and then when you're done, there are little plugs that go in the bottom, and you can take this box over to the printer or just throw it in a closet and store it. And it has a hygrometer and some desiccant in the front so that you can monitor the humidity inside the chamber, and it's got ports on it that allow you to print directly from the dry box. And I thought this was kind of a neat idea. I don't have any idea if this is a particularly good dryer. I've been trying it. It's been working for me. I kind of like the form factor. I kind of like the system. You can buy the heater and you can buy the boxes separately. It's money, but it works pretty well. And it's nice to have a nice little narrow package like this that I can easily set back next to a printer, feed directly from it and then move it out of the way, and it doesn't take up much real estate. Now, I did run into a couple of problems trying to print this filament directly from this dry box on the Prusa XL. The first is the filament runout sensor on the XL. It is a constriction. It pinches pretty hard on the filament. This filament is really stretchy, and it's also kind of sticky. It has a lot of surface friction. So if you run this through the filament runout sensor, it will snag there. And since it's got such a long reverse Bowden tube, the extruder will pull on it and it'll just stretch for a while, but it'll never pull any more off of the spool. And then after a while, it'll just stop feeding. So I found you do have to bypass that sensor. And so you just pull the tube out of it and just feed directly into the tube and skip the sensor. I think you have to switch it off in the firmware on the printer, and then this stuff will feed reliably. The other problem I had was that there was just too much friction in the dry box. So the way this is set up, there's two ways to put in the filament. There are little rollers in the bottom with bearings, and you can drop the spool directly on it and it will roll on those bearings. But what I found is that with all the friction in the long reverse Bowden tube on the XL, even the extra friction trying to roll around the edge of this cardboard spool was too much. It was too rough and it just would not feed. The other option is this plastic axle that you can put through the little drop in, and the spool will run on that. But there's no bearings or anything, and so that's just sliding. And it is a pretty hard, smooth, polished plastic, but I found that even that was too much friction. So what I did is I designed a new axle that uses bearings to support the spool. So I've got a couple of bearings here. I'll put some notes down in the video description about exactly what size bearings these are, and made a new axle spacer and some flanges. Now, one of the things that I had to do, because I'm going to put these bearings on here and the spool is going to ride on the bearings, that increases the diameter and it would raise the spool up. So the way this works, there's a little ridge on this center rib that this axle sits on. And so I put a notch in the end of my axle so that it will sit down, and that notch will go down over that rib, and it'll sit a little bit deeper so that the top of the bearings is at exactly the same height as the top of this axle would have been. So put in 2 bearings and the spacer and the flanges. Drop that in, and now we have a very, very smooth ball bearing rolling action here in the spool. And this reduces the friction to almost nothing. And so all you have left is the friction of going through the PTFE reverse Bowden tube, and this has just worked fantastic for me feeding in the Prusa XL. These are kind of neat. There's a tiny little, like 1.5 millimeter hole in this little rubber cap. You can just stick the end of the filament in that, close it up, and then when you pull it open later, the filament comes right out, and you can grab hold of it and get it out without actually having to open the box. As long as the filament's dry and as long as the feed path is unobstructed, this stuff actually prints pretty well on the XL. You can see there's some little hairs there. That's from cleaning the nozzle on the bed and from probing. But once it actually starts the print, it does a pretty good job. The default retraction settings and the default profiles are pretty nice. And as you can see, it's leaving a very nice, clean, shiny surface. It's definitely not fast, but printing with flexible filaments rarely is. I'd rather have clean than fast. I mean, I'd rather have fast and clean, but if I have to make a choice, I will take clean over fast any day. This print took a little under 2 hours. I think it was about 1 hour and 45 minutes, and the results look fantastic. I kind of expected it to be a little globby from what I was seeing prior to drying the filament, but This looks really, really good. Well, that turned out beautiful. I just cannot complain about that. Got a very nice, smooth, shiny finish here, and it does the thing. When you squeeze it, it squirts air out the end. And you can see the inflation time on this is pretty slow. So if I compare that to a commercial one, you can see this reinflates almost immediately, and this is much slower. And the reason for that is that the commercial one has a one-way valve in the base, so that when you squeeze it, that closes, forces the air out the tip, but then when you release it, it opens and sucks air in the bottom. And we don't have that here, so when I squeeze it, the air goes out. When I let go, the air has to come back in this front. And that's slower because that's a pretty small hole. So it does work though. If I happen to need to clean my lens, I had some black pepper that I spilled into my camera. That smells pretty good. So it works great and it does the thing, but I would like to do something about that reinflation time. So I really would like to put a one-way valve in the bottom of this. And that means 3D printing a one-way valve. And I played around with a bunch of different ideas. I've looked around on the web and seen how some other people have done it. I kind of looked at how some of the commercial ones are done. And I decided that the easiest thing to do here, and the thing that I wanted to try, was a ball check valve. And of course, for a ball check valve, we're going to need a ball. Thought about using steel BB. I thought about using steel ball bearing balls, but the reality is those are pretty heavy and they're pretty small. And I was worried that the small ones wouldn't seal perfectly because the 3D printed surface is not entirely perfect. And I thought a larger diameter ball would have a better time sealing, but a larger steel ball would be heavy and I wasn't sure that the air would move it reliably. So I thought about it for a little bit and came up with this. Plastic airsoft pellets. And these are 6 millimeters in diameter, and they are smooth and round, and they're polished, and they are 0.12 grams. And so I think this would make an ideal ball. It's going to be smooth, so it's going to seal. It's a large enough diameter that I'm pretty sure I can get a 3D printed surface that will seal against this reliably. And they're readily available and cheap. So let's go into the computer and see if we can design something that will work as a check valve using these balls. I have a new version of the bulb duster here in Fusion that has a hole in the bottom and a ball valve inside. And the way this ball valve works is there's a conical surface here in the bottom for the ball to sit on and seal against, and then it has a cage with some openings through it over the top, so that when the air pressure is trying to come in through the bottom, it will lift the ball up and the air can escape through these little windows into the interior cavity. And when I squeeze it and the air pressure inside increases, it'll force that ball down into that conical seat and seal it up. And so this whole thing is like a little pyramid here in the bottom with a cage around the ball. It can't move very far. It can only move about 1 millimeter, but that should be enough. Now, to design this, I just started with the same sketch that I had before and put some more geometry down here in the bottom. Again, since we're going to be revolving this, we just need to design half of it. So I've got a base section here with the conical seat and a wall that's set up 1 millimeter away from the ball. I just sketched in a 6 millimeter circle about at the position where I thought I wanted the ball. Set that up with tangent constraints on this diagonal line so that we could see where the ball is going to be and work around it. So the top part of the cage is again a 1 millimeter thick wall that comes up that is spaced 1 millimeter away from the tangent edge of that ball. And I've just got some geometry in here to define the windows that I need to cut out and a hole that I want in the top. So then for the initial revolve, I went ahead and included the entire volume inside and the entire volume of the valve body so that it would all be solid except for this opening in the bottom where the ball needs to sit. That part will be open so that then when I come back and shell it out, we end up shelling out everything outside of that valve body, but the inside of that is hollow, not because we used the shell command, but because it was hollow before we ran the shell command. So after the revolve, that pocket is already there, And then when we shell it out from the top, it leaves a 1mm wall around there. And since the 1mm wall is what I actually designed in the sketch, the hollow of the inside of this comes down to the edge of that, so we can use profiles like this one to cut the window. So then to cut the window, I'm just using a revolve, and I've just selected that profile, and I've got it set to cut symmetrically, but only partially around the circle, just 20 degrees, and that cuts out a single window, and then I can pattern that feature around the outside. So that gives us 4 windows around the outside of the valve. And then I also want to have a hole in the center. So I revolved a little section in the sketch to create that. And the reason that I want that is so that when we actually have the ball in there, it can't get stuck up against the conic surface here on the top. I was a little bit worried that the ball would come up and it would seal with a little pocket of air above it into this, 3D printed cone. I don't think that's a real problem, but I didn't want it to create any kind of a delay with it falling down because the air couldn't get into that pocket behind it, or if it got stuck in there, if there was some weird forces on the ball because of the air rushing around the side. So I just put that hole in there so that when you squeeze the ball, air will be pressed into that hole and it will easily release the ball from the top of this, just to make sure that it falls down. And then the other major consideration for this is to make sure that this is going to be 3D printable. This is a 45-degree angle coming up here, so that overhang should work fine. Of course, this part is cylindrical, that should work fine. And then the top portion of this is a 45-degree angle as well. Now we've only got about 1 millimeter of space here for the ball to move, so I wanted to make sure that when these areas bridge over, even if they try to sag a little bit, it won't get in the way of the ball. And so this is pretty narrow. How narrow is this? So just from this point to this point it's 1.4 millimeters. So that should be fine. It will try to bridge around that. It will try to bridge that as a curve, and of course it'll just pull straight across. It might sag a little bit, but that really should not be in the way and shouldn't obstruct the movement of the ball too much. I think this will be okay. I think this will print. We can just go ahead and send this to the printer and give it a try. But wait, James, how are you going to get that ball in there? That's a pretty small hole to squeeze in a 6 millimeter ball. And yeah, you're right. And while I think technically you could stretch this enough to get that ball in, that's going to be a really frustrating experience. But we're 3D printing this thing by layers, so what we're going to do is print it part way up, put in the ball, and then finish the print. We just have to put a pause in here to figure out where that's going to go. I'm looking at how this works. This is going to come up. You can use the slider here to look at the layers, or you can actually just use the cursor keys to go up and down by one layer at a time. So you can see here when I print go up to this layer, this is layer what? Layer 39 is where we're first going to try to close that off. So there's that curved extrusion that's going to be a bridge, and that'll work fine. It'll just stretch that straight across and then build on top of it and build up the rest of this. So the point at which we want to stop and put the ball in, we want to go as high as we possibly can to make sure that we are above the top of the ball so that the tool head won't come and collide with it. You can see here that top of that window is above the top of the ball. So if we print everything up to the point where we're about to bridge over and then stop, we should be able to put the ball in and then continue the print. So that's the bridge. I go down one layer and you can come down here, right click on the little plus symbol here and say add pause. And you can put whatever message you want in there and it should display on the printer to tell the operator what to do. And now we have a pause. We can reslice, and the G code will now have a pause at that layer. I think technically it's at the start of the layer, so it'll probably print that and then pause. We can put the ball in, and then it will continue printing, and it'll print the rest of the part. I was a little bit worried that I'd get some stringing between the valve body and the center of the part and the outside wall, but it really didn't happen. The Prusa XL is handling this flexible filament pretty well. This should be the end of layer 39. So the printer should retract the head and pull it back out of the way, and we can insert the ball. Now technically the part is already narrower than the ball, but since it's flexible, we can just snap it in, hit continue on the control panel, and the printer should pick up where it left off. Now you can see there's a blob of filament that oozed out. I should have pulled that off. I'm realizing that now, and yeah, that's me hitting the tripod with the drawer, desperately trying to get a pair of tweezers to pull that off, but alas, it is too late. This stuff is tough, and that blob is stuck hard. I'll try with a pair of diagonal cutters, but you know, there's really not enough room to get under here, so might as well just give up and let it print. The wall is building outward, so the blob's going to mostly be on the inside. It does leave a defect there in the part, but I can live with it, and next time I'll remember to pull that blob off before hitting continue. With the valve structuring here, this print takes about 2 hours, but the results are no less impressive. And here's the part. You can see we've got that little hole in the bottom, and you can just see that the ball is in there. And when I squeeze it, it blows air, and when I let go, it reinflates rapidly. And it is indeed moving in there and sucking air in and out. I think if I plug the end, you can see the ball moving there. It's not moving much, but it's just enough to let air in and reinflate, but to close and capture the air so that we can generate pressure. I'm actually a little bit surprised that that worked on the first try, but it did. I'll take it. If you compare this to the other one side by side, you can see it's definitely inflating faster. And it does the thing. Well, having succeeded, the only thing left to do is declare victory. And of course it fits and the drawer closes properly, but we need a tray for that. Fortunately, it's easy to model one up because I actually have an accurate 3D model for the tool. Drops right in, door closes beautifully. So that's going to be easy to grab, use, and put back. Of course, I'm going to move a few things around here, get this set up the way I want, and that is going to be perfect. If you enjoyed this video, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I would like to know what you think. What is the dumbest little idea that's ever gotten into your brain and prevented you from working on something else? I'd like to hear about it. Thank you for watching.